Of course, like all things IB, there is how we are given the material and then how we actually have to solve it. So I just want to kind of run through the homework problems that I passed out. So one small thing. There are some abbreviations we need to use in IB physics when we're doing problems, and let me just lay them out here. So first of all, let's just make sure that we're dealing with the right distance. I know this is millimeters. Let's convert it to meters. So that will be done by tacking all little 10 to the negative 3. And when we actually fix our scientific notation, that's going to be 4.7 times 10 to the negative 4th meters. And then we have this 9.3 nanocoulombs there. And let's be clear here. This little n here, that means 10 to the negative 9th. That is in the prefixes in the data booklet. So we have 9.3 times 10 to the negative 9th. And let's not forget that we have that letter K that goes into our force formula. That's 8.99 times 10 to the 9th. Now let's go ahead and calculate the force on our charges. So the force is going to be equal to K. Now since these are identical point charges, I'm going to square it, divided by the distance squared. And so that's going to be 8.99 times 9.3 times 10 to the negative 9th. And you know what, let me just be really careful. It's 8.99 times 10 to the 9th times 9.3 times 10 to the negative 9th. And we're going to square that because it's both those charges. They're identical charges, one charge times the other. Normally it's Q1 times Q2, but since they're identical, I'll just square it. And then the distance here is 4.7 times 10 to the negative 4th, and we'll square that. And when we run through those numbers, we're going to end up getting just about 3.5 newtons. And that actually means it's a repulsive force. Now, this is interesting in that we want the force on charge A. And this is an interesting one because there's a little bit of a trick to it. So we have the force on A due to B. That's the electric force. And the way I like to do these subscripts is I like to call A the feeler and B is the dealer. So A feels the force and B is the one that deals it. That's really a terrible way to say it, but students tend to remember it that way. And then we also have this force, from C. So we have a force on A. So A feels the force and C deals the force, and there's an electric force in both of those. So let's be really careful. This is 2 meters, 2 meters. Now, if we use Pythagoras' theorem, this is a right triangle where each of these legs are equal, an isosceles right triangle. From our trig or from our geometry class, we should know that that's 2 radical 2 if you don't want to, again, 2 squared plus 2 squared under a square root. And that gives us a hypotenuse of 2 radical 2, so that's our distance. Okay. Now, what we're basically going to do is we got to do this exactly like we do other physics problems when we have forces. So right here, this angle here is 45 degrees. So the way I'm going to actually calculate this is in the x direction, my forces are going to be FAB, and I'm going to have that one pointing left. And then I'm also going to have FAC at an angle of 45 degrees pointing left. So this goes back to that unit on forces. And then pointing upwards, we have FAC pointing up at sine 45 degrees. And now we can actually set up our equations using the force law that we had before. So we have F is K Q1 Q2 over distance squared. But we actually have to worry about angles because these forces point in different directions. So we're going to end up getting here negative K. And all the charges are 2.5 microcoulombs. Micro means 10 to the negative 6th, so let's go ahead and put that in there. We're going to say 2.5 times 10 to the negative 6th squared. Why am I squaring it? It's because I have this charge here and this charge here, so that's Q1 and Q2, but since they're the same value, I go ahead and square it. And then the distance between the two of them is 2 squared. Okay, minus K 2.5 times 10 to the negative 6th quantity squared. And the distance there is going to be 2 radical 2 quantity squared because we're looking at the distance from C to A. And then in the y direction, what we're going to end up getting is just K 2.5 times 10 to the negative 6th squared over 2 squared. Now let's put in that value for K. That's going to be 8.99 times 10 to the negative 9th. You know what? We'll do that in the next line. So I'm going to end up getting 8.99 times 10 to the negative 9th times all this other stuff. I'm going to simplify. What I'm going to do is I'm going to put in 8.99 times 10 to the 9th here. And then I put it in here. And I'm going to do a little bit of calculator work, which I'd like you to try to do on your own as well. And basically what we can say is simply that it's going to work like this. So 8.99 times 10 to the 9th times 2.5 times 10 to the negative 6th quantity squared. And we'll divide that by 4. So that's going to give us here 0.014, and that's again negative. And you know what? I got to be really careful here. I said that this is 2 squared. It's not. It's 2 radical 2 squared because we're dealing with that direction. Minus, and here when we put in our numbers, that's going to be a similar number divided by, I'm going to end up getting here negative 0.007. And here this will also be 0.007. So we end up getting here negative 0.021. 0.007 newtons in the y direction. Now, to get the value of the force, when we add x and y components, the total force is going to be the x part squared plus the y part squared under a square root. That goes back to our old knowledge of forces from the last semester. So 0.021 squared plus 0.007 squared and so basically we've got 0.021 squared plus 0.007 squared. And then we'll just take the square root of that, and we should end up getting about 0.021. I got 0.022. Now, we can get an angle for this. It turns out this goes back to our forces stuff from last semester. If I actually take 0.007 and divide it by 0.021 and get that angle, and actually this is the tangent of the angle, then we'll end up getting that theta equals the following. Ends up being about 18 degrees. They get 15, but it's close enough given the numbers that we're working with. All right, now here it says calculate the electric field this far away from this charge. Again, the electric field is simply going to be given by this formula. We just need to be careful that we're using the right number. So 8.99 times 10 to the 9th times 25.6 times 10 to the negative 9th. Remember to shove that in whenever you see nano. And then here it's 0.245 centimeters, so that's 0.245 times 10 to the negative 2 quantity squared. So there we go. Right. And when we actually, we'll just calculate all this out here. And so we'll get and actually I should be careful, that's 0.0245. So, oh, I see what I did there. No, it's in fact 0.245 times 10 to the negative 2 because I'm converting. So, yeah, that's how I do it. And so that ends up getting me about 9.4 times 10 to the 7th newtons per coulomb, or newtons coulombs to the negative 1. All right, now here, these problems, this is a doubly challenging problem because what you want to do is you actually want to figure out one point. There will be, so these are the charges. It turns out that the point where the field will be 0 will be somewhere in between, and you actually have to go ahead and try to calculate that. And let's see, 2 millimeters from charge B. And okay, these two questions that actually might be good for us to try to do 4, 5, and 6 in class together. 1 and 3 are really the ones that I'd like you to try to do on your own. 4, 5, and 6 are a bit challenging. We can actually talk about those as a class together.